Hi, my name is Stephen Sadler. I'm the Chief Scientist at Durridge Company. Durridge has been at the forefront of professional radon measurement for the past 2 decades or more now. And in that time, we've seen our flagship RAD7 radon detector put to good use in a variety of different applications, from public health to oceanography to even dark matter research. But one application that's been around in the scientific literature for nearly as long as the RAD7 itself, but for which we haven't seen that much real-world uptake, is the mapping of non-aqueous phase liquids, or NAPL, contamination in soils and aquifers in the environment. So I was delighted when the organisers of this workshop asked us to prepare a presentation about this. So many thanks to them for that. So the outline of this talk is going to begin with an introduction to NAPL and radon, in case anybody is unfamiliar with those terms. I'm going to move on to talk about mapping and quantifying NAPL contamination in the vadose zone using measurements of radon and soil gas. And then move on to mapping and quantifying NAPL contamination in aquifers using measurements of radon in water. Finally, we'll have a summary. So what is NAPL? Well, as I mentioned, it stands for non-aqueous phase liquids. These are environmental contaminants that are immiscible in water, tend to be fuels like, for example, diesel, kerosene, petrol, but they can also be things like chlorinated solvents and mineral oils. So these are typically found at sites like abandoned industrial sites or petrol stations and that kind of thing. They can be divided into two categories. So LNAPL, where the L stands for lighter than water. This occupies the vadose zone, but it can penetrate all the way down to the water table and to the saturated zone. And the second type is DNAPL, where the D stands for denser than water, so denser than 1 gram per centimetre cubed. And this tends to sink down to the bottom of the saturated zone. So the DNAPLs are things like the chlorinated solvents and mineral oils, whereas LNAPL tends to be the things like the fuels. So the goals and applications of NAPL measurements. So first of all, is to map the spatial extent and the degree of the contamination for the purposes of planning remediation activities and assessing the risks associated with it. As I mentioned, examples of types of site where you might where you might want to map NAPL is military sites, industrial sites, airports. And it could be sites that are in use or sites that have been abandoned. So the traditional solutions for measuring NAPL are listed here, along with their drawbacks, so we'll go through them one at a time. The most obvious one is just direct detection, either of the NAPL itself through drive point profiling or core sampling, or of the organic vapours that come off it, like VTEX, for example. Drawbacks to this are that it can be expensive because many samples are needed to cover spills, which can be patchy. And it's necessary to take samples to a lab for analysis, so you can't do the data analysis on site. Second technique is the detection of organic vapours that are produced from biological breakdown of NAPL in the soil or aquifer. So these are substances like, for example, methane or carbon dioxide. It takes time to accumulate these gases in the soil because of their biological origin, and therefore you can't use this for new spills. Finally, the injection of artificial tracers like sulfur hexafluoride. So the drawbacks of this are probably quite obvious. For one, you're perturbing the system that you're trying to measure by adding something new to it, and there are possible legal headaches associated with adding these artificial gases into the environment, and they can also be very costly. So what's the alternative? Well, radon. So radon is a colourless and odourless, naturally occurring radioactive gas. It's produced from the decay of radium-226, which is itself part of the uranium-238 decay chain. So uranium-238 is one of the primordial radionuclides that's found sort of everywhere in the Earth's crust. Radon is chemically inert because it's a noble gas, so it doesn't tend to interact chemically with anything in the environment, which means that it tends to be conservative. And it has a short half-life of just under 4 days, which makes it an ideal tracer of short-term processes that occur on these sort of timescales. It's a non-destructive and non-invasive tracer because it's already present in the natural environment. And the reason why it works for measuring NAPL is because it has a strong affinity for NAPL. So it sort of preferentially partitions out of water or soil gas into the NAPL contamination. And you can actually measure this using an instrument like our RAD7. So you can see this in the picture on the right here. There's a radon percentage curve. This is just a sketch, so it's kind of for illustrative purposes. Overlaid over NAPL contamination, which has made its way down through the vadose zone, which is shown in light grey, all the way into the groundwater, which is in the dark grey section at the bottom. And you can see that because the radon is taken up by the NAPL in the region of the spill, the radon levels that you would measure there, either in the aquifer or in the soil, are reduced. So the rest of the talk is going to be concerned with going over that in a bit more detail. So yeah, the two techniques that I just mentioned are, number one, measuring NAPL contamination in the vadose zone by measuring soil gas, which we'll start with, and then we'll move on to measuring and mapping NAPL contamination in the saturated zone by measuring the radon deficit in water samples. Okay. So for the soil gas measurements, you need a continuous radon monitor, for example, our RAD7, and an accessory like a soil probe, which so you can drive into the soil to take a sample of the soil gas at a given depth. When you're choosing an instrument for this type of work, it's important, obviously, to look for high sensitivity because the more counts per unit radon concentration that you can get, the lower your statistical uncertainties and the more precise your measurements. But precision is no good without accuracy. So you also want an instrument that's that can discriminate the radon signal from backgrounds, such as, for example, long-lived polonium-210. Background that gets plated out on the surfaces of any radon detector, just because it's further down in the radon decay chain and long-lived. So the RAD7 can do this background discrimination. And radon-thoron discrimination is another important one. So there are instruments in the market that are unable to do that in real time. And the problem with that is that you then need to wait for around 10 minutes at the start of each measurement to allow the once you've collected your sample, you need to wait around 10 minutes before you begin counting to allow the thoron to decay. So this introduces a small delay into each measurement, which 10 minutes may not seem like very much on the face of it, but if you're measuring a site that's several hectares and you have a sampling grid of a few tens or even hundreds of sampling points, that 10-minute delay can really add up. So the RAD7 can make precise reading around plus or minus 10% uncertainty at the typical sort of soil gas radon concentrations every half hour. And the nice thing about this setup is that once you've pumped the sample from the soil into the instrument, this takes place in the first 5 minutes of the half an hour measurement. The instrument can actually then be, the probe can be pulled up an instrument will continue to count the sample as you walk to the next site and even set up the equipment for the next measurement, so that once the half-hour counting period is finished, you're then immediately ready to go for the next one. Okay, so here's an example of radon mapping of NAPL in the soil. This is an abandoned airstrip in Germany, where there was a known NAPL spill in the past. So you can see that denoted by the white dashed line on this plot on the right-hand side. This was measured using traditional core sampling techniques to locate the NAPL spill, diesel in this case. The black points are a grid of 209 soil gas sampling points that were sampled with equipment similar to what we saw on the previous slide. And the grayscale that you can see is the radon concentration in the soil at a depth of 70 centimetres as reconstructed from the measurements made at those black data points. The reason why 70 centimetres depth is chosen is because above that depth you can have interference with the radon concentration from meteorological effects. So, for example, day-night heating and cooling is one, or changes in atmospheric pressure kind of suck radon out of the ground or suppress, push it back in. So, as you can see, there's a strong negative correlation between the NAPL and the radon concentration. I should say, sorry, that the radon, high radon concentrations are shown darker on this grayscale plot. So the light areas there are areas of low radon concentration, which correspond nicely with the known extent of the NAPL spill. Okay, so going one step further, we can actually try to quantify the amount of NAPL contamination in the soil. I don't want to go into really any detail about the maths here. I've just put the equation on this slide to really talk about the different terms that appear in it. The two most important ones are circled there in red and purple. So the red is what you measure, the radon concentration in the soil pore space. And the term in purple is the target variable, so the NAPL fraction. Well, in fact, this isn't exactly what you're after, but this is easily related to the total NAPL contamination. So you can see other variables that appear in the equation are the density of the mineral matrix, the porosity, the total fluid saturation, and the radon partition coefficient, both between water and soil gas and NAPL and soil gas. So those last two, the K factors, can be looked up in the literature. There are values for those. The other parameters need to be either measured for the specific site that you're investigating, or they can be estimated as well. So what are the pitfalls and limitations of this technique? Well, mineralogical heterogeneity is one big one. So if you measure the background radon level at a site, removed from the site of the NAPL spill, and assume that this is applicable to the whole site, you may be making an invalid assumption there, because there's a possibility that the radon levels that you measure in an uncontaminated version of the site would vary spatially somewhat. Similarly, permeability heterogeneity. So as well as the radon emanation from radium-bearing rocks or things in the soil, there can also be variability in the permeability of the soil. So there may be the same amount of radon there, but it's not able to actually permeate the soil and reach your sampling point. So that would give you a sort of non-uniform background distribution across your site as well, which can confound your results. We've already mention meteorological interference. The way to get around that one is just sink probes deeper than 70 centimetres. Rain can affect radon concentration, so if possible, it's best to make these measurements in fine weather, but if not, its effect is understood and can be accounted for. So since the K values that we saw on the previous slide as inputs to that equation are similar for different types of NAPL, so different fuels or etc. This technique can't tell you precisely the nature of what's there. You still need to take a few core samples to get that information. And you can see this illustrated in the table on the top right of this slide. So the K values for 3 common NAPL contaminants shown there, and they're all fairly similar. So they're hard, if not impossible, to disentangle. And finally, this technique is limited to NAPL contamination within the diffusion length of radon in the soil that you're looking at. So in dry sandy soil, this is around 2 meters, but in water, it's only a few centimeters, which means that you can't detect NAPL below the water table with this technique at all. And if you have sort of a wet or clayey soil where the diffusion length is a lot shorter than this, then you either need to have a much denser sampling grid. Well, you do need to have a much denser sampling grid, otherwise you'll miss. You stand a chance of missing the sort of blobs of NAPL contamination in the soil. So this slide just illustrates the heterogeneity problem. So it's taken from a paper by DeSimone et al. So on the left is the target site where the contamination is, and on the right is the area where they took the background samples. So in this case, they've taken 6 and I guess averaged them when they've applied them, subtracted them from the real data. And I just wanted to draw your attention to the fact that the background area is more uniform than the contaminated site, but there is still there's still quite a bit of variability in the radon levels in that background site where there's no NAPL contamination. So this really is a nice illustration of how other factors can affect the radon in the ground as well. It should be noted that the colour scales on these two pictures are not comparable. So the left-hand one starts at 2,000 becquerels per meter cube, the right-hand one starts at 22,000. So the level of variability is nowhere near as high on the right-hand side as the left-hand side. But still, there is measurable variability there that is not associated with NAPL contamination. Okay, so moving on to measuring and mapping contamination in the saturated zone. So for this, you need, again, a radon and air monitor, like the RAD7, and also an accessory that allows you to take water samples from the aquifer and exchange the radon from the waters of the air phase and then measure that with the radon detector. You can see that you still need to drill sampling wells to collect the water for this, so it's not quite as convenient as the soil gas sampling technique, where you don't need any pre-existing infrastructure there. You can just take the soil probe and start making measurements. The way this works is the RAD7 contains an internal pump, and it bubbles air in a closed loop through the water sample to exchange the radon into the air, where it's then measured. The whole process takes, again, half an hour. So the first 5–10 minutes are doing the bubbling and the radon transfer, and the last 20 minutes is the counting time. All of this equipment is very portable, so these measurements can be done in the field, or you can choose to just collect the samples in the field and take them away for later analysis at your convenience. If you do decide to make the measurements later, it's very important to note the exact date and time that the sample was collected, because from the moment when the water is taken out of the ground and is no longer in contact with the radium-226, which is supporting the radon level inside that water sample, the radon is beginning to decay. If you leave it any sort of length of time between sample collection and sample measurement, it's important to know how long that time was so that you can then make a correction for the radioactive decay of the radon in the sample. And like I said, this will give you precise and accurate results in 30 minutes. Okay, so this is an example of some radon measurements that were, again, made at a site where there's known NAPL contamination. This time we're looking at a disused petrol station. The top pane there shows the known extent of the NAPL contamination based on soil coring, again, just deeper this time. And the bottom panel shows the radon concentration in water, well, reconstructed from water samples taken at these roughly 15 sampling wells, labelled P in the diagram. Okay, so we've seen how the radon can be used to map the NAPL contamination in the aquifer, and now we're moving on to try to quantify it. Similar parameters go into the model as we saw for the radon in soil case. However, in the aquifer, we also need to take account of the fact that there's some groundwater flow that can act to smear out the radon concentrations that we measure. So the equation that you can see in the top right is for the simple case of no groundwater flow. Things get a little bit more complicated when you introduce the flow. You end up with 1D sort of models like this one in the bottom right, which is this is distance along the direction of groundwater flow on the x-axis, and the radon measured in the water samples on the y-axis. So, and the actual NAPL contamination zone is shown by those black boxes. So you can see as you hit the zone of contamination, the radon level drops significantly. So this is like by a factor of 3 or so. And then over the following 2 meters or so, they rise back up to the background levels. So similarly to the soil case, just to estimate or measure the other parameters in the model, and then adjust the level of the NAPL contamination that you input into the equations until the model fits the radon data that you've measured. So pitfalls and limitations of this technique, well, they're pretty similar to the soil case. So the heterogeneity of the mineralogy and water permeability can again have an effect. In this case, you still need to drill sampling wells, so it's not quite as convenient as I mentioned. Again, since the coefficient of partitioning between the water and the NAPL is similar for a wide range of different NAPLs, you can't find out from this exactly what is there. And finally, the mixing of groundwater between the contaminated zone and uncontaminated zones can lead to an underestimation of the contamination. And this is a particular problem when you have particularly fast-moving groundwater, where the residence time of the water in the region of the NAPL is not long enough to allow the radon to fully partition out of the water and into the NAPL. In that case, you'll measure a higher radon concentration than you would have done had it had time to complete that partitioning, and therefore you'll underestimate the amount of contamination that's there. Okay, so in summary, radon measurements are an alternative to direct core sampling for mapping and estimating the amount of NAPL contamination in soils and aquifers. There are plenty of real-world examples of this in the scientific literature over the past 2 decades, but as I say, to our knowledge, it hasn't been applied too often in anger. It's complicated by factors including heterogeneity in mineralogy and permeability. Can't tell you the exact nature of the NAPL because of the similar radon affinities between the different types of NAPL. But even if quantitative measurements are not possible, radon maps can allow you to precisely target remediation efforts to the most contaminated locations. So even if you don't know how much is there, you know pretty well where it is, which is good. And it can be much faster, cheaper, and more convenient than traditional methods like core sampling. Okay, so this is just the references, maybe illegible, but if you would like a copy of the slides, please feel free to contact me. Thanks for your attention.